56 tomorrow morning at a distance of 104,000 kilometers, which is safely away from any material. Triton closest approach will be at 6:16 daylight time Friday morning. We will enter Earth occultation at 6:45:20. We will enter Sun occultation at 6:45:39. We will exit Earth occultation at 6:48:18. This is a very short occultation. It's only around 3 minutes. And we will exit Sun occultation at essentially the same time. All in all, I think the orbit, the spacecraft is performing admirably. The ground stations, including all of our various cooperating antennas around the world, have been performing almost flawlessly. By the way, the little noise you saw in the images yesterday, believe it or not, was rain in Spain. But other than a few minutes of that, the whole ground system has been performing admirably, and the spacecraft is doing exactly what we wanted. So everything's right on target.
Well, this is the day. I hope you've all figured out when you're going to sleep. I haven't. As of 9:20 this morning, if I could have the first slide, please, we were still in the solar wind. We were somewhere up here, ahead of the bow shock, presumably, although we have seen some rather unusual conditions in the region overnight, starting at late yesterday afternoon, which is posing some bit of a puzzle. But I think we do feel confident that we're continuing, at least as of a few minutes ago, to see the supersonic solar wind. So that really suggests we're still here. We should be getting close to the bow shock. That would suggest the field strength at the equator is unlikely to be larger than about 0.4 Gauss. So it's the kinds of numbers that we've been talking about the last few days. But any minute we'll have our first contact with the Neptunian magnetosphere. All right, I'd like to just give you some highlights of what's coming up. This is, as I said, the day. I don't intend at all to go through every single thing we're going to be doing, just to give you some computer graphic impression of some of the things which will be showing up during the next 24 hours on the screen. Not everything will be coming back, as you know from the timeline you've been given. Some will go on some of the best images of Triton, for instance, will actually come back a day later. This is about 1 o'clock this afternoon. That square that you see is the wide-angle frame, so we're now close enough that Neptune will actually fill the wide-angle frame. Could you focus that a bit? I think it's not quite focused. And, of course, in the wide-angle camera, we have additional methane band filters so that we can make now high-resolution images of Neptune, a resolution something on the order of 100 kilometers per line pair, 66 miles or so per line pair. So that's about 1 o'clock this afternoon. You'll be seeing these wide-angle images of Neptune. Then about 45 minutes later, we'll have our best image of Nereid. The best image is not all that great because Nereid is really very far from Neptune, about 55 miles per line pair. That's 145. That would be the best one. Then between 3 and 5 o'clock today, we'll be doing and there will be images coming down at the same time, but the principal activity will be an accurate measurement of the temperature of this particular spot in Neptune's atmosphere. That's the spot where we'll be doing a radio occultation, and I'll show you in a few minutes why that spot is important. We want to compare the temperature measured by the infrared instrument with the temperature profile determined by the radio occultation experiment. So that's between 3 and 5 o'clock. There'll be a series of images associated with that long infrared observation. 5 to 5:30, we'll have a set of images on the north hemisphere, northern limb of Neptune to try to study, again, the scattering properties of the atmosphere. Those will be narrow angle images, and we'll have really quite spectacular resolution. And then we will also have some retargetables. This will be about between 5:45 and 6:45 late this afternoon. 2 sets of retargetable images of the rings. Resolution about 5 miles per line pair, 2.5 miles per pixel. These will be among the best, highest resolution images of the rings of the outer ring arc. And during this time period between 5:45 and 6:45, we've also managed to insert into the sequence a high-resolution image of 1989 N2. So that will be coming down around dinner time. We also have the stellar occultation of the rings, Sigma Sagittarius, where the photopolarimeter will actually track the star. This is around 9:30 this evening, and going behind the outer ring arc and the inner ring arc both. So that's an important activity for accurately measuring the profile, the density profile of the rings. At 11 minutes after 10 approximately tonight, we start color images of Triton. These will be our last images of Triton before our closest approach, and will be in color. The resolution will be something on the order of 10 kilometers per line pair, 6 miles per line pair. So these will be really beautiful images, even though we'll get much better ones in a few hours. These images this evening will already undoubtedly have a lot of geological interest. Like I say, I don't know when anybody's going to have time to sleep. We have a ring plane crossing at about midnight, the ring plane being right about here. So we cross the ring plane, and about the same time, we expect to see the maximum intensity in the trapped radiation environment, and we also will possibly detect with the plasma wave instrument some of the fine dust that we often find in the equatorial plane of these giant planets. That's at just almost exactly midnight. Then at this, the telemetry then is off and remains off for the critical experiment that we do. This shows the spacecraft at the ring plane crossing. We head then for the radio, so we turn off as we go through just as we go through the ring plane, and this is the critical period for the radio occultation. This is this latitude right here is where we've been measuring the temperature that I mentioned earlier, so that we can make the comparison with the temperature that radio science measures at this point. Because we actually don't turn off the transmitter, we just turn off the data transmission. The transmitter remains on, dedicated to the radio occultation probe of the atmosphere. While we're behind Neptune, we will actually point the antenna of the spacecraft in a series of segments toward the limb at just the right angle, so that the radio beam will be refracted by the atmosphere in just the right direction to arrive at Earth. So we expect, in fact, to continue receiving signals from the spacecraft throughout this entire period that Voyager is behind the planet. And that allows us to probe most deeply into the atmosphere with the radio beam, perhaps as far as deep as 2 to 3 atmospheres in pressure, perhaps down to the top of the lower cloud deck, but certainly we hope below the top cloud deck of methane ice. So that's a critical activity. Of course, you won't see anything on the screens during that time. It will all be coming down as uncoded, pure radio data. That's between about 1:08 tomorrow morning and 1:57, all in local time. Then, of course, we do have a series of images as we approach Triton. This is not exactly the configuration for the images that will be coming down in real time. We will be getting some real-time images of Triton between 3:40 a.m. and 5:25 a.m. Those should really be spectacular. Following that, we'll have another series which will go on tape recorder for playback still later. Then at 6:50 tomorrow morning, we do the same kind of occultation of Triton's atmosphere. That is, we watch the sun with the ultraviolet spectrometer. This is the slit of the spectrometer as the sun cuts across Triton, and so we can measure very accurately the methane atmosphere which is there. And we'll also, from Earth, be measuring the effect of the atmosphere on the radio beam, just as we did at Neptune. This occultation, Neptune occultation, lasts almost an hour. This occultation lasts a whole 3 minutes. You'll hardly notice it in terms of the downlink data. So that's just some of what's ahead. As I say, this is it. This is the 24 hours we've been waiting for. Okay, I would now like to show one last thing. Caltech and JPL have designed a supercomputer. It's called the Hypercube. It's actually 128 computers arranged in an array to operate concurrently, giving the power of a supercomputer with actually just an array of many regular computers. As I say, it was designed and built here at JPL with a lot of input from Caltech campus. And the Digital Image Analysis Lab has been working with the Hypercube group here to do the complicated calculations you need to take the images which come in, which have to have a lot of correction done to them in order to project them so that they look, if you like, real life. And I have this morning the first product, and they'll be working on more products. The first product that's come out of this activity. This is really the first time that we've had the capability to do this kind of image reconstruction in this kind of time scale. You need basically a supercomputer capability. And so this film you're going to be seeing is essentially the first of the products. So if we could have the film. There will be 6 rotations, so we'll be able to see it several times, each rotation taking about 6 seconds. Now this is a single image which is rotating, so it's not dynamical. In other words, you're seeing the same thing over and over again. You're not seeing 6 separate Neptunian days. Eventually, of course, we should be able to do this with the atmosphere evolving rotation by rotation. That's what we're really aiming to be able to do. But you can already see, of course, the small dark spot and the great dark spot. There are also some blems on the camera which show up, which haven't been removed like that thing. But you can also see the streamers, the cirrus, which is associated with the great dark spot at this particular latitude. You can also see that there's a cirrus streamer up in the northern hemisphere. Your eye begins to pick up some patterns with this kind of a presentation that aren't necessarily so obvious when you sit and stare at the images one at a time. And of course, once we can actually make this into a time-lapse movie where the atmosphere is actually moving, and we have that data, it will really be a very valuable tool as well as a very beautiful thing to look at. Okay, I think Brad Smith's up next.
Good morning. We found ourselves this morning in the position of trying to analyze the images that came in yesterday afternoon and last evening so that we would have something to say about them this morning, while at the same time being terribly distracted by extremely high-resolution images that kept showing on the screens and diverting our attention. We are getting very, very close to the planet now, and almost every imaging frame that comes back is extremely exciting. I have a number of slides I would like to show this morning, so I think it's best just to get right into them. And the first is a very high-resolution image taken of the great dark spot. Again, this was all possible courtesy of Andy Ingersoll and his group of forecasters, who really did an outstanding job on the great dark spot and allowed us to put the images exactly where they should go. You can see a lot of structure now in this image. A lot of structure in the high cirrus type clouds, but still not much down in the spot itself, and that may take more detailed processing than we've been able to do at the moment to bring out any structure that might be down in there. This is the highest resolution image now that the narrow-angle camera will take of the great dark spot. It's over near the limb. The very, very smallest clouds that you see in this image are only 25 kilometers across, and at this image, I believe, was shuttered only about 20 hours before closest approach. So this is the highest resolution image. You can see the limb of the planet up here. It's quite foreshortened because it was close to the limb, and it's just showing that all of these clouds are breaking down into very, very fine structure. That essentially is the message in this image, which has now been map projected to bring out some of that structure. And it's making it extremely difficult for the dynamicists. The dynamicists are trying to track these individual clouds, to look at a particular cloud and then see where it is a few hours or maybe 10, 18 hours later, and having difficulty locating them, because what we're seeing here are not clouds that are rapidly moving. As the air around them is rapidly moving. This is in a very high velocity region. There are undoubtedly very strong shears, but these can be considered analogous to the lenticular clouds that you will see hanging over mountains. They seem to be just stationary over a mountain, but the air that's going through them is going quite rapidly. And what's happening is that as the winds blow through this region, they get deflected upward. Now, whether that is due to the great dark spot itself, we don't know that, but it quite probably is, that there's something about that dark spot that deflects these winds upward as they go up, carrying volatiles like methane in them. They reach an altitude where those volatiles condense out and form clouds. Then as the wind moves on, it descends and it goes down into a warmer region, and these little ice crystals of methane sublimate, they disappear, evaporate. And so the cloud appears to be stationary, even though the winds are moving very, very rapidly through this region. The next slide illustrates the problem. Again, these are map projected, but these images are only 2¼ hours apart, and yet you can see there are some major changes that have taken place in only 2¼ hours. This cloud right here, for example, which isn't even seen in this image. Is it this that's moved to here, or is it just this one has faded out and a brand new cloud has been created in its place? And those are the kinds of problems that we're having, and it's the reason that we're a little bit slow this time in getting actual velocities from the cloud motions. This is now a high-resolution image of the smaller dark spot, the one that's been called E2. Those of you who were around early this morning may have seen an extremely high-resolution image of that cloud filling the field of view of the narrow-angle camera. We'd like to say we predicted that, but I have to be honest, it just by chance happened to fall right into the center of one of the frames that was taken while the infrared instrument was scanning up and down on the planet. But it's an absolutely magnificent photograph, and we should have a processed version of that available for you tomorrow. What this is showing is what we suspected, that the bright cloud in the middle of this dark feature is high. It's convection. It's moving upward. This is a false color image where we use ultraviolet as an additional color, and in general, whatever looks very blue is deep, and what looks somewhat pinkish color here is high. So it's just a demonstration of height for the particular clouds in the center of that dark spot. There are other ways of getting height. This is a false color image which has been generated using the wide-angle camera. It's an orange frame and a short wavelength methane filter and a longer wavelength methane filter, all together to produce false color. Normally, these images are analyzed not by creating an image, but by studying the numerical values that come out of such an image. But it does provide some graphical evidence of height. And in this particular image, if anything that's white is is very high, and what's perhaps pinkish is intermediate in height. And you see it has a sort of a orangish brightening around the limb. The reason for that is that material near the limb is reflecting light before it has a chance to be absorbed by methane, and the reason for that is that there's just very, very long path lengths through the atmosphere near the limb, and the probability that it would reflect a grain of ice and bounce back up is much higher near the limb. Well, there are other ways of measuring height, and this image appeared to us yesterday afternoon, and what we are actually seeing are cloud shadows. These are some of the very high cirrus-type clouds, and you can see right along the edge of each one is what is almost certainly a shadow caused by these clouds. Now, this, to the best of my knowledge, is the first time that Voyager has actually been able to show or see cloud shadows on any of the planets that we've looked at. So this was quite a surprise for us, and quite a pleasant surprise, because it allows us to make some estimates of the heights of these clouds. And I guess we've got a bad slide up there somewhere. Push it down in there. Okay, this shows about where those clouds are. They were down in the South Polar region. This is the South Pole, and the sun is shining in this direction and casting shadows along the southern margin of the clouds. Well, by looking at these images, it's possible to make some estimates of height, because we know exactly what angle the sun is shining at, and we can measure the projected distance of the cloud to the shadow, and that gives us a measure of how far it is from the cloud down to this more or less uniform haze layer, or lower cloud level, upon which the shadows are cast. The measurements so far are really quite preliminary, but the number turns out to be quite extraordinary, something of the order of 50 kilometers between these very high clouds, these cirrus-type clouds that we've been talking about, 50 kilometers from there down to this lower cloud deck. And there were some estimates from the team this morning that they could be as high as 75 kilometers. And here is just another view of a different part of the planet, but again showing some of these little high puffy clouds casting shadows on the lower cloud deck. Well, turning from here to the rings, I have. Okay, we need to push that one down too, if you would. It's a better piece of artwork, what I had showed you yesterday, trying to show the relationship between the more or less continuous ring, the outer ring, which is composed of several fairly bright segments, and then a longer and more diffuse region. And as of yesterday, I believe this was the region within which we had not seen any ring material at all. But we did take wide-angle frames last night, and I'll show you one in just a moment, in which we have now seen material extending further along here and further along here, and now there's only about 10% of the ring in which we have to date been unable to see anything. So I think that it's almost certain now that this is a complete ring, and that the amount of material over here is just so very, very thin that over a certain range, anyway, about 30 degrees or so, cameras have not yet been able to record any material in there, but certainly it has to be there. This is 1979, 1989 N3 and 1989 N4. This now is one of the images that was recorded this morning. Here again, I mentioned yesterday, there are artifacts that appear around bright objects in the field of view. This is 1989 N2. This is trailed out because of its orbital motion. This is a star, and here you can see the outer ring. Now this is the trailing edge, fairly sharp, but with material which extends on, and this is the leading edge, getting more and more diffuse as you go along, and here is the inner ring curving around like so. And as had been suggested in some of the images that we took, that we acquired over the past few days, this ring also seems to show some structure. Certainly not nearly as varied as the outer ring, but it's not perfectly uniform as we go around. We have two new satellites, and here they are. This is the planet, 1989 N5 and 1989 N6, and out here 1989 N3. And you can see quite easily just from these photographs that N5 is quite a bit fainter than N3, and N6 is even fainter than N5. And if I can have the first view graph, this will now give you a listing of the satellites as we understand them right now. So this is the temporary name. Eventually this IAU committee will put formal names on these objects, but that won't happen until later this year. The orbital radius, the distance from the center of the planet now. The orbital period expressed in hours. The orbital inclination, that is the angle between the plane of the satellite and the planet's equatorial plane. For almost all of them, a value very, very close to 0, but this last one showing an appreciable inclination, certainly a measurable inclination of roughly 4.5 degrees. It certainly shouldn't be taken as 4.5. We just didn't have a little half sign to put in there on the machine that set up the graph, but 4.5 degrees, probably plus or minus a half degree, so that needs to be pinned down further. And here are the estimated diameters of these objects. Now, they have not been resolved. The smaller ones certainly have not been resolved. And so what we did was just to assume, and I think it's a reasonable assumption, that they all have roughly the same reflectivity. And so by measuring their brightness, that gives us an estimate of what their diameters are. So we go from 89 N1 up around 420 kilometers in diameter, all the way down to the most recent two, which are about 90 and 50 kilometers respectively. And I will make copies of this, or the Public Information Office will make copies of this so that you can pick them up afterwards if you like. Well, we can have the view graph off now. These are a couple of images of N1. We're actually beginning to resolve it. I'm showing you two of them to show that the shape is not due to some peculiar properties of the Vidicon or due to image smear. It is really out of round, and it's probably getting up to about the largest satellites that you can imagine that won't pull themselves into a spherical shape. And if you were going to try to draw some conclusions, what does all this mean? One conclusion that you might draw is that this object, because it is out of round, has remained rigid since its formation. Now, we don't know when it formed, but had it partially melted, it probably would have pulled itself into a more spherical shape. So it's probably reasonably pristine since its formation, whenever that was. This summarizes, in the slides that follow, summarize some of what we know right now about Nereid and 1989 N1. In comparison, you'll notice that if our estimates are correct here, Nereid is not the second largest satellite in the Neptune system, but it is instead 1989 N1. The albedos are similar. Nereid is around the 10% level, 10% reflectivity, whereas N1 is very dark, reflecting only about 6% of the light that falls on it. There have been questions over the past few days, does Nereid vary in brightness? There were ground-based observations made a year or so ago which suggested that its brightness varied over something like a magnitude and a half, which is a factor of 3 or so in brightness, and that is not observed. The brightness amplitude variations are less than 10%. I don't know exactly what the number is for N1 right at the moment, and neither did the person who put the slide together, but it's apparently a small variation. We don't know what the period of Nereid is, but we would be surprised if it was synchronous. That is, the inner satellites are more likely to keep always the same face toward Neptune. Triton does this, but Nereid is in this very peculiar orbit that takes it way out from Neptune, and it would be surprising if it did always keep the same face toward Neptune. Almost certainly N1 does, and so we show a estimated rotation period for it being about the same as its orbital period. Notice that Nereid has this very long orbital period about Neptune, approximately 1 year. These are some of the geometric albedo, essentially reflectivity measurements that have been made as a function of wavelength for Nereid, all running somewhere up around 10 or 12% here, and no trend with wavelength. That is, this would be blue or violet in here, this would be, well, sort of a blue-green, let's say, and this would be out in the green region. And so it's fairly neutral. And this is consistent with this darkish material that we see in the outer solar system. It is dark and quite neutral in its color. That is, it tends to be a dark gray color. We don't yet have color on 89N1, but you can see shown here that it is definitely darker than Nereid. And just one more slide showing how Nereid gets fainter with increasing phase angle, the phase angle being the angle between the sun and the observer as seen at the object in question, in this case Nereid. What this does illustrate, it's just further illustration that this satellite is not varying in brightness, because these are taken at different times, but they fall along a fairly nice straight line, whereas the ground-based observations that had suggested light variation would have had it ranging from the top to the bottom of the screen up here. This now is our fairly recent false color image of Triton. False color in that we have used ultraviolet for the short wavelength, violet for the intermediate, and green for the longer wavelength. And the purpose of the false color is to show what tends to be bluish or whitish, and you can see along these margins of along the dark areas, the reddish areas, this blue color which is persisting. This little region in here, for reasons we don't fully understand, is darker in ultraviolet. That makes it show up somewhat more orange in this particular image. And you can see the detail beginning to just become finer and finer. This image is, I think, our most recent image now of Triton. And it's taken through a violet filter, and we've put a map grid over it so you can see just about where the South Pole is. This is the equator up here, so the equator is running sort of along like so, and the terminator is along over here. And again, finer and finer detail. There are some members of the imaging team who believe that they are seeing craters, but they certainly haven't convinced me of that yet. But again, we don't have to wait very long before we really know. And then this is the color image which goes with the violet that I just showed you. And again, one can see the reddish color of the darker areas up around the equator, and the overall pinkish color of the bright regions, which, as we've said a number of times now, we believe is due to processing, chemical processing of the volatiles, the methane and others perhaps, due to high energy particles. The final view graph, I guess, we can have that up here now. I've just indicated, will indicate for you when some of these high resolution images will be getting down on the ground for these new satellites and Nereid. So we will have some fairly good images of the 1989 N1, 4 of them coming down Thursday, about noontime tomorrow. And, sorry, today? Oh, right. Okay. Well, it's a shorter wait than I thought, okay. I'm glad you told me it was Thursday. I thought it was still Wednesday. Okay. Nereid coming in this afternoon. This will be the very highest resolution images of Nereid. And I warn you, don't have great expectations because Nereid was just way, way out in its orbit at the time these images were taken, and they aren't very many pixels across. The highest resolution images of N2 will be coming in this evening, 3 images. Then the very highest resolution image of N1 will also come in this evening, but I put down that it's a partial image, and that is that before the whole thing gets played out, the window goes away and the tape recorder has to stop running, and so I don't know, maybe it'll be 2/3 of a frame. We're not exactly sure, but not to worry, because those who want to hang around until the early hours of tomorrow morning will replay it and get the entire image down. So this is the schedule. This is the time that they should appear on the monitors. That's all I have. We can make copies of this available also to you afterwards.
Before we take questions, I have a couple of announcements I'd like to make. For those of you who aren't staying all night with us, I suggest that you arrive early tomorrow for a number of reasons. Parking is one, and other logistics. Among a large group of distinguished guests that we have visiting the laboratory tomorrow will be the Vice President, Mr. Quayle, and we expect a large turnout. There will be a speech by Mr. Quayle on the steps of the tall glass building across the mall from the auditorium at 8:40. That's open to photo coverage, still photo and television cameras. Then he will appear down here in the auditorium at about 9:10 to 9:15. We're not sure the exact time. At that time, he will take questions from the press. And in addition to that, we are going to start a rebadging activity today after the press conference. So please check with the PIO folks out in the newsroom. You will have to exchange your badge for a new one. And be prepared to show your press credentials. Also, we're going to have a rather short question period today because our panel has a commitment elsewhere. Maybe we can talk them into coming back later in the day, but we will have to keep it short. Patrick?
Could I ask, please, have we yet any precise evaluation of the density of Triton's atmosphere, please?
Linda?
Hello? Okay. Linda Doran, San Gabriel Valley Tribune. Do you have any determination yet whether the moons that you've discovered so far could be in a position to be shepherding the rings?
There are 2 satellites associated with the 2 rings. Those are N3 and N4. there have been no other satellites observed in the vicinity of those two rings.
Yes, right down there in the first row.
Horst Rademacher, doesn't work. Does it work?
Yeah.
Horst Rademacher, Frankfurter Allgemeine Zeitung, West Germany. I have a question for Ed Stone. A couple of days ago you told us that you were going to take ultraviolet images or ultraviolet measurements from the southern hemisphere to look for auroral activities. Did you find any, number one? And number two, you mentioned that at the very beginning of your presentation today that you found some anomalies or anomalous results near the bow shock that you are going to fly through. What are these anomalous results?
We don't know we don't understand what the magnetic field certainly had some significant changes to it, and this afternoon we're going to have a discussion to try to understand it. It's unlike anything we've seen before. That's the impression that I have, yes. No indication yet of any aurora. Again, I hope to hear some more this afternoon from everybody. It's not booming bright, that's clear.
Bob Bazell on the aisle.
This is a question for Brad Smith, and this is logistics, not science. We have a schedule from the Public Information Office that indicates we won't be getting any real-time pictures from 11:24 p.m. tonight until 3:40 a.m. tomorrow, because other equipment on the spacecraft will be playing back. You just mentioned that we'd be getting a picture at 1:50, and now I'm even more confused than I was before.
And you've confused me as well. I don't know the answer to that. That's the information that I took down from the timeline. There would be a tape replay at that time to send that image down. So
Generally correct that there will be no real-time pictures coming in from about midnight tonight till about 20 to 7 tomorrow morning.
No, there will be real-time images before 20 minutes till 7.
It doesn't sound... You said no real-time images from when to when?
11:24 p.m. to 3:40 a.m.
I think that's not correct, but I don't have the material with me yet.
Well, we would, those of us who need these images would really appreciate it. Correct.
We'll try to sort that out, Bob. We'll do it today. Lee Dye.
Lee Dye, LA Times. Brad, if N1 is larger than Nereid, why was Nereid detected from Earth and not N1? Is it just a matter of albedo?
It goes way out away from Neptune, and it goes so far out that in a typical field of view of an astronomical telescope, Neptune is out of the field of view when you're looking at Nereid. N1, on the other hand, is so close that it's just simply lost in the glare of Neptune, and that's why we couldn't see it from the Earth.
Tom?
Tom Elias, Scripps Howard Newspapers. Is this working?
Yeah.
For either Dr. Stone or Dr. Smith, I wonder, why are we seeing cloud shadows here and not on other planets? Does this suggest anything at all about a planetary surface by any chance? And about Triton, do we have any new ideas about why we're getting blue?
What it's saying about the Neptune atmosphere that apparently has not been seen on the other planets is that there are very high clouds and then a relatively clear region down some considerable distance to a cloud deck below that. As I said, perhaps 50, maybe even 75 kilometers. It's just an indication of a structure in Neptune's atmosphere that we have not seen in at the other giant planets. With regard to the blue color, we've talked that around a bit more. There may be some other explanations, and we're pursuing those, but the explanation that I gave that it could be due to Rayleigh scattering by very, very small ice crystals seems to be still reasonable.
Jonathan?
Looking at Triton, we're seeing it looking way down in the southern hemisphere, so it's really hard to tell what's going on in the north, but I am reminded from that little bit that we're seeing, are you seeing what may be a marked hemispherical, north-south hemispherical asymmetry, like sort of as distinct as that on Iapetus, for instance, or are we maybe just seeing a, you should pardon the expression, Triton in equatorial band?
We can't answer that because we're just seeing what we are seeing. Clearly, the region in the south is bright. The darkish regions start a little bit below the equator and move up northward from there. But we haven't yet had a look further north. We will see further north as we approach Triton early tomorrow morning.
As far as you can tell from looking closely at those images, as far as we can see up at the top, looks like dark all the way to the edge.
Yeah, but we can only see up to about 20, 25 degrees north at the moment.
Lee?
Lee Siegel, AP. Norm, a couple things. You didn't mention a close encounter distance for Triton, if you could give us that, and when the second entry into the second Earth Sun occultation, is. And finally, on behalf of one of our newspaper members, what would happen if a speck of dust hit Voyager?
Well, it depended on how big it was and how fast it was moving and where it hit, I think. But we've probably been hit before. We don't want to encounter a whole lot of those. So it really is problematical what would happen if it was going fast enough and had enough mass, it could do some damage.
Norm, I could add that actually if it's really dust, if it's micron-sized particles, micrometer-sized particles, so we have in fact sensed exactly those particles every time we've gone through a ring plane of one of the giant planets. Dust doesn't bother the spacecraft, BBs would.
Lee, relative to your first question, I just gave that sheet of paper that I had written all the things down on to the Public Information Office people to have transcribed. I do have the distance of Triton closest approach on there, so it'll be available. My recollection is it's in kilometers, it's like 39,700 and something. Here we go.
I think that's it, isn't it?
All right. 39,872.
To the center.
That's the center, right.
From the surface?
From the surface, you have to subtract, 1360?
1360, roughly.
1,360 kilometers.
Also in the last row on this side.
Richard Harris from National Public Radio. For Dr. Stone, yesterday, as I recall, you were predicting that the spacecraft would pass into the magnetosphere of the planet around midnight last night, and apparently it has not yet. What does that tell us about the strength of the magnetic field? Or
well, it's a combination. It means the field is not as strong as it might have been, and that perhaps the solar wind conditions are somewhat stronger than we thought they might be. I mean, the solar wind, after all, is like weather. And so the combination of a stronger wind and a weaker than expected or weaker than possible magnetic field would all result in a later bow shock crossing. You may remember I did give you a chart showing you a whole range of crossing times depending on how strong the field was.
Gilbert?
I wonder from a celestial mechanics point of view, I'm sorry, Govert Schilling, working for Dutch newspapers. From a celestial mechanics point of view, could there be any influence from the inclination of the new moon N6 on the confinement of the material in the ring arc, or would it be too far away?
I think it's too early to say. What is critical, the exact locations of moons and arcs are critical. They can't just be inside. They have to be precisely at some particular location inside. So I think it's too early to say. One has to know very accurately exactly where the moon orbits and exactly where the ring orbits. And the team is working on that, but they haven't yet pulled it all together. I wouldn't want to exclude it at this time.
Rick Gore?
Brad, that inclination on the new satellite, 4 degrees, 2.5 degrees, what implication does that have, and why would it be inclined?
Well, when satellites form around a planet or are captured or whatever, they may start off at any particular inclination. Then there's a process by which planets tend to force material into the equatorial plane. Now, it may have started at a high inclination and still has some residual inclination left over. It may be maintained in that by some interaction with the other with the other satellites. But there's a tendency for things to be pushed into the equatorial plane. And that has implications for tonight, by the way. Any debris that's around the planet tends to force it into the equatorial plane, and that means that so-called ring plane crossing would be the most hazardous time for the spacecraft.
Over here on the center aisle.
Yes, Olivier de Goursac from the Figaro and the CNES magazine. Do you have an exact diameter right now for Triton? And a possible density you might think of something from the interior of the satellite? Because it seems icy, or have you... but do you have correct values right now with images by the number of pixels you have? And could you at least give us a kind of diameter?
The radius is approximately 1,380 kilometers. That may be better determined now than it was a few days ago, but it can't be far from that number. As far as density is concerned, we have to know the mass first, and that will come out of the encounter tonight, so we will have a density shortly.
Linda?
Glenda Chu from the San Jose Mercury. I have two questions. One is, I understand that the magnetic field people at about 8 o'clock last night believed that they had crossed the bow shock and were very excited about it, and in fact believed that the magnetic field was maybe 5 or 6 times stronger than previously believed. It sounds now that you believe that that did not happen, and in fact that other instruments didn't confirm that. And I wonder if you could elaborate on what appears to be happening there with this weird phenomenon. The second one is, I understand also that there's been some confirmation due to albedo measurements of methane ice on Triton on the surface, and I wonder what that says about the possibility of there being other forms of methane on the surface, such as liquid and so on.
Well, first of all, indeed the magnetic field did change, and that's part of this unusual property that I was discussing, which we still don't understand. But the solar wind itself, which moves at 400 kilometers per second, or about 1,000,000 miles per hour, did not change. And certainly the classical signature of bow shock, which is a supersonic shock, is there's an abrupt change in the solar wind speed. And so there is a puzzle, which we hopefully will be sorting out as to what was happening. But I think we don't have a classical shock in the sense that the solar wind has gone subsonic. In terms of the methane ice, there was ground-based data which told us there's methane ice. That's not, I think that's not a new result. And the temperature there is much too cold for liquid methane.
Yes, over on this aisle.
Heather Cooper, Pioneer Productions in London. I have a question for Brad. Brad, I appreciate you're having problems measuring the wind velocities, but is there any indication you're getting these high-speed jet streams as you found on Saturn?
There are winds which have velocities which are comparable to what we've seen on the other planets, that is in the range of several hundred meters per second. But how narrowly confined they are at the moment is, we don't have information on that. It requires a lot of measurements and getting around this problem where the clouds seem to change on short time scales.
Yeah, I just got a note that the film which I showed this morning, it was the first time really I'd seen it, and I want to make sure that the people who really did the work get the credit. And the people who did the work to get the film put together is the image analysis group here at JPL under Gary Solomon, who's the group supervisor. And that's the group that was using the Mark III Hypercube along with the Digital Image Analysis Lab. I'm sorry if I didn't get the story straight when I showed the tape.
In the second row, over on this side.
Bob McDonald from Canadian Broadcasting Corporation. I have two questions. One for Norm. Yesterday you told us that your accuracy in trajectory was plus or minus 33 kilometers. Are you any more accurate today? And can you give us an analogy of just how accurate that is in some way? And the other is for Dr. Stone. Your experiment to maintain contact with the spacecraft while it's behind the planet through this refraction, you've never done that before. Is there something you're expecting to get from that experiment that you haven't tried before on the Voyager mission?
Yesterday, I think I told you that our uncertainty in the estimate of where we were going, that is, if you think you're going to spot X, our uncertainty is a little circle around that, was about 33 kilometers at the Neptune aim point. As of today, it's about 30 kilometers, which basically says that's about as good as we're going to do it, which isn't bad. It's within 20 miles of the point we aimed at, 3 billion miles away. So it's not bad shooting. The time of flight uncertainty is we are about a little more than 4 minutes early. We did not try to correct that with maneuvers. We had the ability to modify the sequences to take into account the fact that we're 4 minutes early. So we didn't try to change the time of flight. We just let it go. But our uncertainty in that estimate is down to a little more than 1 second now. So we believe that time is accurate to about 1.2 seconds.
Yeah, we did at Uranus, in fact, exactly the same experiment and did maintain contact throughout the track around the limb, and that allows us to probe much more deeply in the atmosphere than is possible if we just use the entrance and exit of the occultation event. I'd like to add one other thing. I see this note I got that was an 8-node hypercube, not a 128 node. I certainly didn't get all the information, did I? Only 8 nodes, so if we had the 128, they could do it in real time, I think.
And today is Thursday.
And today's Thursday, yeah. Just think what it's going to be like tomorrow after we haven't had any sleep.
Back in the radio area, Terry.
This is Jim Banky of Florida Today. You've mentioned when some of the high-resolution images are coming in. Could you say of the images yet to come, which ones you're looking most forward to seeing? When will they arrive here? And could you reveal what some of your Voyager science team people will be doing tonight? Is everyone staying up all night tonight?
Well, for the imaging team, I can't say that everyone will, but many will, because our next to most interesting images of Triton will be coming down in the early morning hours. We are continuing for a while to keep getting higher resolution images of Neptune, and what's interesting among them, they're all interesting because they're all showing things that we haven't seen before, particularly with a wide angle. It's going to be a very exciting evening, and most of us will be up there watching everything that comes in.
First row on the far end.
Carlos Byers, Houston Chronicle. When you're discussing the winds on Neptune and the different velocities, what are some of the maximums that you're looking at there? And secondly, Brad, do you think what are the prospects for more satellites?
Let me pick the satellite thing first. Steve Sennett, who is with the navigation team and also a member of our imaging team, is the one who has been spending most of his time looking for satellites. He has so many other duties to perform. That's why we're a little slow getting this information out. I think his comment to me yesterday was we're reaching the bottom of the barrel, but still there are many images where the very faintest suspects have not even been identified yet. So one would certainly not want to say at this point that we've seen all the satellites we're going to see. On the other hand, we have no active suspects at the moment. And I'm sorry, the first question dealt with the wind velocities and what,
various levels that you're seeing. Any input on that at all?
I mean, differences in velocity, or are we talking about heights in the atmosphere?
No, I was on velocities. If you've been able to develop anything at all, we know that they're very high, but I was just wondering.
Yeah, the velocities are high. We're talking typically of velocities that we've seen on each of the major planets in the outer solar system we've looked at. The velocities seem to be up in this range of a few hundred kilometers per second. And that's rather peculiar because there's an enormous range of energy that's being dumped into these atmospheres from Jupiter on out to Neptune. The velocities all seem to be up in that same range. Now, what's interesting is how narrowly confined, how narrow are these jets. We saw some extremely narrow jets on Jupiter. Whether we'll see, say, such narrowly confined jets on Neptune hasn't been determined yet.
Also in the first row.
Let me come back to this magnetosphere thing again. You said there is no shock where the solar wind gets subsonic. Did I understand you correctly?
Well, we haven't found it yet. It's almost certainly there. We haven't gotten there yet, as of at least 9:20. It may have happened since.
Kelly?
Stone, do you expect that Voyager will be passing close enough to Neptune to go through its ionosphere? And if so, what manifestations would you anticipate?
No, we're some 3,000 kilometers up above the North Pole, so we don't expect any serious problems with the spacecraft at all from an atmospheric point of view.
Yes, right across the aisle.
3,000 miles, sorry, 5,000 kilometers, yes, thank you.
Tom Siegfried, Dallas Morning News. Could you tell us, Dr. Stone, at the exact moment of the closest encounter, what instruments on Voyager will be doing what right at that point?
At closest approach, all of the instruments will be on. The tape recorder will be recording the data because there will be no downlink telemetry. The transmitter will be left on, but without any modulation. So for the radio science occultation experiment, but all the experiments will essentially be recording data for later playback.
What about the cameras? Where will the cameras be pointing?
Well, I think at the moment of closest approach, I don't believe there are any images being taken at that moment. No.
Too fast.
We have a question from the other JPL viewing area.
Don Dixon, Orange County Register. Could you estimate the magnitude of the rings as observed from Voyager's current position? Would they be brighter than 6 magnitude?
They would not. I think they would not. They're, in terms of stellar magnitudes, the limit for the Voyager cameras is something of the order of ninth magnitude or so. They're just barely showing up in the narrow angle, perhaps in the wide angle. It's a difficult thing to say. If you were riding aboard the spacecraft, you might just barely be able to pick them out with your eye.
The far last row, or on the end.
Is there any thought that the solar maximum or solar flares is accounting for the anomalies that you're seeing in the magnetosphere?
Well, I think it's too early to say. We had very quiet solar wind conditions for the last several weeks, and so it's a puzzle at this point. It's just too early to say.
I understand that we're going to have to conclude about 20 minutes after 11 or about 11:25 at the latest. Is that right?
Yes.
Okay. So we'll take all the questions we can. David Chandler.
David Chandler, the Boston Globe. Dr. Smith, you said that the image that you showed this morning was the highest resolution we're going to have of the great spot. Do you have any estimate yet as to the speeds of the circulating winds in that spot? And since you've got your highest resolution image, what's your sense of whether how closely you're going to be able to nail that down?
What we see clearly are these high-level cirrus-type clouds. That isn't necessarily telling us what is happening down in the dark spot itself. There's certainly not been any. There's not been any structure in there which just really stands out. It's going to take a bit of rather sophisticated image processing to bring out any structure that may exist in the spot itself. And we have not had time to do that yet.
Do you think it's going to be possible to get those speeds though?
If we can indeed pick out recognizable features, then we can measure the velocities. Yeah.
Lee?
Dr. Stone, is this on? Could you just briefly, what's Neptune's gravity? Could you quantify it for us? And second, could whichever one of you or all of you would like to wax philosophical for a moment about how you feel after 12 years and being here at the last planet?
I don't know the gravity I can't tell you off the top of my head. We can look that up, but I don't know what it is. 1.14 times Earth. There's the answer. Thank you.
You know, Lee, we're all caught up in the encounter right now. You know, it's all going to sink in the next few days. That would be the time to ask the question.
Kevin?
In looking at yesterday's image of the Great Dark Spot and also the images you showed today, I begin to see something that looks very much like overlapping ellipses, with the overlap regions darkened relative to the rest. Could you say something about that?
Well, we've noted that patterns do tend to form, and the structure of that spot changes dramatically. In that sense, it's very different from the Great Red Spot. And there are features which seem to overlap others. All I can say is we've noted the same thing, but haven't been able to draw any conclusions from that yet.
Yes, in the last row.
Dr. Stone, in your presentation, you called attention to a little circle that had been drawn on Neptune. I'm not sure I understood what the significance of that circle.
That's the field of view of the infrared measurement that's being made of that particular spot in the atmosphere, which is the spot where the radio occultation, the radio beam comes out of the atmosphere after occultation.
In the back, on the other side, standing.
Thornton, KGIO Radio. I know you probably don't want to look beyond Neptune at this point, but realistically, beyond this encounter, how long do you think, knowing what you know now, the Voyager craft will stay together and remain viable?
Well, if nothing breaks, and that, of course, can't be predicted, we have enough power, fuel, and so on to keep tracking the spacecraft for another 25 to 30 years, at which point Voyager 1 will be some 130 times as far from the Sun as the Earth is. May well be in the interstellar medium by then.
Also in the back.
Peter Bond for the Independent newspaper in England. I understand that the Great Dark Spot is comparable to a hole in the atmosphere. You're looking deeper. But I also understand that on the false color image you showed, the center of the spot showed white, which you said was for a high-level atmospheric feature. Could you clarify that for me, please?
We now have evidence that there is a cloud layer at some particular height in the atmosphere of Neptune, and that there are these bright white clouds that may be 50 or more kilometers above that surface. Probably what we see is the Great Dark Spot is down at that lower layer, maybe 50 to 75 kilometers below. It isn't necessarily a hole. It may be a low-pressure region, or it may actually be a high-pressure region. In order to determine which it is, we need to measure its vorticity, whether it's cyclonic or anticyclonic, and that has not yet been done.
Standing on the left side.
Carl Hodge, the Arizona Republic. Will there be a time even before the images come in when you can say that you have indeed reached the predicted closest encounter? When will you know for sure you're there?
I think you could safely say that 101.39 or whatever it is will be the closest approach.
We'll know by looking at the clock, I think.
Right, right.
That's right.
Trudy?
Trudy Bell, IEEE Spectrum. Are there going to be any other images that may reveal more about the structure and the behavior of the scooter? Or have you been able to do any analysis on the ones that you have that give any more idea about it?
It has been targeted for high-resolution imaging. I don't know right at the moment how successful that targeting was, but certainly it was targeted for high-resolution imaging.
Yes, right next to you there, Ed.
Dr. Smith, Roger Hutchins from England. We're seeing in dramatic detail the resolution growing on the storm features you've been seeing for months, but we're not seeing an increasing comparable resolution in other structure in the atmosphere. I know you haven't got all the data in yet on analysing the haze layers, but can you give us an idea as to whether it's giving you a clue about the nature of the haze layers, bearing in mind that Uranus also didn't resolve as we got a lot closer?
Yeah, certainly that's one of the objectives of this investigation. Many of the images that will be useful are taken fairly close to encounter, and actually some when we have passed Neptune and look back. And there are images which have been selected sort of specifically to work that problem. But as I've indicated, not all of the data are in yet, and I have no information at the moment about the structure other than these two fairly distinct layers that were demonstrated by the cloud shadows.
On this aisle.
Terence Murtagh, BBC Northern Ireland. Yesterday afternoon in the briefing they indicated you were planning on the outbound to get an image of Triton with the limb of Neptune in the foreground. Any indication at what time we could expect to see that?
Sorry, I don't have the information. Perhaps we can get it for you.
David?
Neptune's color is very similar to that of Uranus, and for similar reasons, but many of the photos that have come out in the last few days seem to have a significantly deeper blue color. Is that a real difference between Neptune and Uranus, and if so, what does it tell us about its composition?
Well, all of the blue color, regardless of whether we've got the right color or not, is due to two effects. One really scattering, and the other, a more dominant effect, the absorption, selective absorption of certain parts of the spectrum by methane gas. It's not all that easy to define true color, because the filters that are used on the Voyager spacecraft have different sensitivities to particular spectral regions than the human eye does. The human eye begins to lose its sensitivity in going from blue down into violet. So we don't see violet as well as a camera might, and that tends to boost the violet color, or the deep blue color of these images. We could, of course, make corrections for that, but in the very short turnaround time that we have for producing materials for press briefings, we just haven't been able to do such an elegant type of processing. Oh, is it different? No, I would, just from looking at the spectral reflectivity, Uranus and Neptune are almost the same.
Toward the back on the left side here, Ed, right there, the blue shirt.
Andrew Yee, Science North. Dr. Smith, can you say anything about the composition of Nereid based on the color and albedo information?
No, not precisely. The reflectivity is 10%. It's very similar to the reflectivity of some of the darker satellites that we're seeing around Uranus. It is just more of this dark material which seems to like the outer part of our solar system. Some of the best estimates, guesses that we can think of as to what it is that they're volatile materials, the ices that tend to form in the colder parts of the solar system that have been darkened by radiation.
Govert? Good.
Dr. Smith, I just wondered about the light blue color on Triton. Isn't that just what you would expect, being there's such a big, huge blue planet in Triton's sky? Couldn't it be some sort of Earth light like the same we have on the moon?
If it were in a particular position, that I suppose could be an explanation when we're seeing a reflection of blue Neptune in the images on the surface of Triton. But where it happens to be, no. If we were seeing any reflection there, it would be black sky. So what we're seeing is really on the surface, and it really is a blue color.
We have time for just 2 or 3 more questions. Glenda?
Glenda Chu. I noticed on the old timeline for this afternoon that there's something called a phase function that is supposed to determine the amount of heat that's coming out of the interior. I wondered if that would be enough in itself to
to make some kind of determination of what is in the planet's interior? And if not, do you expect to get that kind of information from this encounter, and when would you know what is in there and what form it's taking?
Phase function. These are images, you say?
I don't think it said whether it was an image.
We'll have to check it out. I don't think there's anything immediately in the images that's going to tell us much about the interior of the planet. That has to come from an analysis of higher order gravitational terms that in the gravitational field.
The first row down here.
Luther Young from the Baltimore Sun. I have a question for Dr. Smith. Is the ring arc scenario probably dead now? And if it is, do you have any philosophical observations about the theory that was created to explain ground-based observations?
Well, I mean, look, the arcs just... The reason that people talk about arcs is because they saw an event happen on one side of the planet and they didn't see it happen on the other. And the most logical conclusion is that if there are rings, they're not complete. They don't go all the way around. Now, it was a handy term to use at the time. It was necessary in the literature. It was necessary for one astronomer to communicate with another. Did you see an arc at this point, etc.? What's going to happen now? Well, my guess is probably that term will sort of go off into the sunset. Although we do have to consider that this outer ring is a very peculiar ring. When you forget about all this extremely thin material that may now close all the way around, that still leaves a section of that ring about 35, 40, 45 degrees long, which is just very different from any other part of it. So in a sense, it's a semantical argument. And I can't predict what kind of nomenclature, what kind of terminology will go on into the years ahead.
We'll take one more question. Which hand did I miss before? Marguerite?
Marguerite Corriveau, Ozali Films in Montreal. This is a question for Brad. Concerning the clouds that you were looking at, you showed us two comparisons where you said it was very difficult to follow the structure of a particular cloud going from one image to the other. I wonder, do you have planned a series of images that can then be put into a time-lapse movie that will allow you to follow such structure more easily?
Essentially, we do that, although we don't actually prepare a movie. We make measurements on frames, and that all gets fed into a computer. The computer does the thinking for us. But what we're seeing, if you were looking down on the Great Dark Spot right now, just sitting up above it and looking down and watching it for a few hours, I think what you would see is not so much clouds moving around, but one that forms and disappears, another one that forms and disappears. It's because of these waves, and they're not giving us a measure of the velocity. It's just telling us that there are very high-speed winds going through there, that they're being deflected up and down, quite probably by the dark spot or something associated with it, and they tend to come and go rather than move. We've got to look for other types of features if we expect to actually be able to measure the winds.
That's all the time we have. Thank you very much, and please don't forget the rebadging exercise. We'll try to make it as easy as possible.